So on to 12-3. Now we're starting to get into the actual calculus or the roots of calculus and what it wants to achieve. So first we're going to talk about this idea of what's called a tangent line. Now, a tangent line, if you guys are way back from geometry, when we did circles, a tangent line would, oh shoot, that's a terrible one. Way back when we did circles, a tangent line, it's just as bad, it's whatever. A tangent line intersects that circle at exactly one point, and it's actually also perpendicular. So the same idea in philosophy holds true for graphs. So a tangent line, it intersects a graph at exactly one point. And the cool thing is that it actually gives that exact slope for that exact spot. Not all graphs have the exact same consistent slope. So for example, if I have, again, I know I default to this example a lot, but the parabola is a really good example. If I did slope from here to here, it would be different than if I did slope from here to here. There's an exponential graph curve. But if I were to draw a tangent line at exactly this point, I would know the slope exactly right there. And that's what a tangent line aims to do. So for example, again, in the real world, let's say we had, I don't know, a global pandemic where a disease or a virus, bacteria thing were to potentially cause people harm. It would go like this. It'd be an exponential graph. You start with, 0 or patient 1, and then you get to 4, and then you get up way up here, like us at the time recording this video in China, where you get 80,000. It's not a linear or flat curve, it's an exponential growth model. So we use these to potentially find the slope and the rate of change, or how many people at this particular point we expect to get infected, or the change in difference of it. That's what a tangent line does, and is used for. Well, how do we solve for that? Well, we kind of cheat a little bit and use limits. And then we take the crux of what it's actually meant to do. It's technically a slope line, so we try to get a little cute with it. Now I said it works for just one particular point, but to create a slope we have to cheat a little bit and use 2 points. So let's say this first point is x, is our x coordinate naturally, and then f of x, where whatever x we plug into our equation, f of x is what we get spit out. Okay. Our second point, I'm running out of colors, use pink, that's fine, is some new value, let's say x plus h, because it's still going this way, so it's plus some value, h, the difference between our first coordinate and our second coordinate in the 8x spectrum. And then it would be f of x plus h, because I'm not plugging in the x value anymore to get an output. I'm plugging in whatever my x is originally, plus my h difference. Again, you guys remember slope way back when from geometry, and then even from algebra 1. Slope is just rise over run, or y2 minus y1 over x2 minus x1. Well, if I just gave you 2 coordinates, I could just plug those in. So my y2 would be f of x plus h minus f of x all over x plus h minus x. Okay, well my top, I can't really do anything to break that down, but on my bottom I can see that I would get x plus h minus x, so that's just the same thing as h. And this is the slope formula type deal that we use to create these tangent lines. Again, it's also called instantaneous rate of change. we use that idea, but we have to spruce it up a little bit. In front of all of it, we get the limit as h approaches 0. So because we use these 2 points, we want h to be as small as possible to where we just get that 1 point. So again, we use the idea, the limit as h approaches 0 of f of x plus h minus f of x all over h. Now we can already see that we're going to have some problems with h in the denominator and h approaching 0, so we're going to have to get cute and do some algebra with it, and it should all work out in a perfect world. Knock on whiteboard. But that's where we're coming from. H is just that second distance between those 2 points, and we want h to essentially be 0 because then we only get that 1 point because that's what a tangent line is. Okay. Well, enough of that. Let's go into some examples and see how it works algebraically. Example 1, slope at a point. So let's say, well, first of all, we need an equation. So let's say we get y equals x squared, and then we also need a point. Let's say 1, 1. So if I were to graph it, I'm looking at what is the slope exactly right here. What would this slope be? Which obviously is going to be very, very different the slope of, let's say, 416, which, as we see, would be way more vertical. Okay. So we can just take our idea and plug those in. So I get the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, I don't have an h value, and I typically won't, but I do certainly have an x value. I have 1. So I can plug in a 1 everywhere I see it for x. So I get f of 1 plus h minus f of 1 all over h. Now again, remember, all f of something means I just plug in that into my equation. My equation is x squared. So instead of having f, I can just square this part. So I get 1 plus h squared minus, well, I already know what 1 squared is because it's my f of x, but minus 1 all over h. Now all I just got to do is do the algebra. 1 plus h squared. Remember, that just means 1 plus h as the quantity squared. So I get 1 times 1, which is 1. 1 times h, which is h times 1, which is h. And then h times h, which is h squared. And I'm just going to order it in combined like terms. So I get h squared plus 2h plus 1, and that's right here. So just rewriting what I have h squared plus 2h plus 1 minus 1 all over h. Okay. Next step's pretty self-evident. We just need to combine terms. So I get 1 minus 1, so I get h squared plus 2h over h. And now all I have to do is this idea that if I'm dividing by h, as long as I have an h in every term on top, I can just do it. So I divide every term by h. I get my limit as h approaches 0 of h plus 2. That's all that's remaining, and I still have my limit part from the beginning. Now, can I finally direct substitute? Yes, because I'm not going to have a negative radical, and I'm not going to divide by 0, so I can just direct substitute. So my limit, or my slope, my instantaneous rate of change there, my tangent line would have a slope of 2. 0 plus 2. Okay, now we're going to talk a little bit about velocity. So those of you in physics will have a pretty ahead version of this. So the idea is that velocity is just distance over time. If we want to get technical with it, it's just a speed in a given direction. So 60 miles per hour. I would go 60 miles in an hour, my distance over my time. So essentially that boils down to is f of b minus f of a all over b minus a as my slope. Where if I have a line and it was linear, for example, I get a comma f of a and b comma f of b. Just my first coordinate and second coordinate. So it's just, the idea is exactly what you think. It's pretty straightforward. Okay, so let's do an example of essentially slope. Now the big thing to note is this is technically average velocity. So say we're given an equation like f of t equals negative 1.3 t squared plus 12t for a runner, and they want to know between 2 and 3. 2 and 3 hours. Just how far did they, or what was their average speed during that time? Again, the big thing to notice is the average velocity. The reason I can tell it's average velocity is because we're given 2 points. We're trying to find the velocity over this time where we're given a different coordinates. If we were just given one coordinate, like the previous example, we could find the instantaneous velocity. We haven't quite got there yet. Okay. Well, I already know that I'm going to have 3 minus 2 on the bottom, because I get my a term, my b term. But I need an f of a and an f of b term. So I'm going to plug these in, so I get, let's see, negative 1.3, 3 squared plus 12 times 3 is going to be my f of b minus, I gotta plug in 2 in those spots. Negative 1.3, 2 squared plus 12, 2. So let's see, 3 squared times negative 1.3 is going to give me negative 11.7 plus 36, 12 times 3 plus 36 is going to give me 24.3. 2 squared is 4 times negative 1.3 is going to give me a negative 5.2. 2 times 12 is 24, so plus 24. Going to give me an 18.8, and I have to subtract in between. So 24.3 minus 18.8 is going to give me 5.5. And that's all over 3 minus 2, so 1. So an average of 5.5 units per hour. My guess is miles per hour. I didn't even look at the distance quantity, but yeah, units per hour, my answer would just be 5.5. That'd be the average velocity. Does that mean they went to 5.5 the entire time? No, maybe they started off really fast and then later slowed down, or started off really slow and later sped up, or had a kick in the middle. You never really know. When you run, just like a tracker or something, you're not always running the exact same speed the entire time. So again, that'd be average velocity because I'm given how the two endpoints and a function that models their speed. Now, if I were trying to find instantaneous velocity, what would I do? Well, I would use the same idea for tangent line as I did for instantaneous velocity. If I can model velocity with an equation, I can certainly do an instantaneous version of that with a tangent line. So, same thing works. We use the limit as t approaches 0. Is it t approaches 0 or is it h approaches 0? H approaches 0, my fault. H approaches 0. But instead of f of x, we have f of t because velocity is a function of time. Plus h minus f of t all over h. So all that changes, instead of having an x in those spots, we have t's. Okay, so again, instantaneous velocity, it just tells us the speed at a very specific second. Oh, I actually skipped a problem I wanted to do. So hold on to this for a second. I'll just do it again. I'll do it again. That sounds better. Okay, so we'll write into instantaneous velocity. So again, let's say we're given some function. So example 4. F of t equals 2,000 minus 16t squared. And we were given at the time where t equals 5. So again, I can just go right into it. Let's see, I get the limit as h approaches 0 of f of t plus h minus f of t all over h. Well, I just plug in t plus h, in this case 5 plus h, everywhere I see a t into my function. Remember, this is f of 5, this is 5 plus h. Well, nothing's going to happen with my 2,000, so 2,000 minus 16 times the quantity 5 plus h squared. Because that's what's happening. My 5 plus h is plugged in for my t squared. That's going to be 1 on my top. Then minus 2,000 minus 16, 5 squared. Again, all over h. Well, let's do this side first. It's probably going to be a little easier. 5 squared times 16 gives me 400. So this is the same as 400. So I get 2,000 minus 400. So this entire expression is 1,600. I'm going to need to do this 5 plus h squared part because order of operations. So 5 plus h, 5 plus h, 5 times 5, 25, 5 times h, 5h, h times 5, 5h, h times h squared, and I'm just going to reorder and combine terms, so h squared plus 10h plus 25. Now again, the important thing is I'm not quite done with this because it's negative 16 times that expression. So I'm going to multiply everything times negative 16. So I get negative 16h squared minus 160h. 25 times 16, oh, it's going to be like 400, I know it. Negative 16 times 25, negative 400. So that's that whole expression. And then of course I had this 2,000 out front. That's this whole expression. Now I'm just going to move over to the other side of the board because I'm running out of room here. So I have, let's see, 2,000 minus 16h squared minus 160h minus 400 minus 1,600. much getting to the spot where I should try to combine like terms. So I get 2,000 minus 400 would be 1,600, minus 1,600 again, which would be 0. So all I have left is negative 16h squared minus 160h all over h. Now again, just like before, because I have h in every single expression, I can cross it off. So boom, boom, boom. I get the limit as h approaches 0 of that, which would be negative 16h minus 160. So in this case, I can direct substitute. So I get negative 16 times 0. So all I get is negative 160 would be the instantaneous rate of change of this function at t equals 5. So my guess is, typically when you have a negative 16, just from my experience, it's talking about gravity and projectile motion. And then, like I said, there's one more example I wanted to talk about actually that wasn't in my original notes. And I apologize. It's actually example 2. It's slope of a graph. Every example we've done so far has gotten us down to one exact answer. And that's not always going to be the case. So, for example, what if I have just an equation y equals 4 over x, but I don't have a coordinate? Well, sometimes your slope just turns into a graph, a function itself. What I mean by that is, again, we can still do our same process where I get the limit as h approaches 0 of f of x plus h minus f of x over h. Well, again, I'm just plugging x plus h into my equation everywhere I see it, so my new top is 4 over x plus h instead of x. And this one would just be 4 over x, and then over h stays. Now in this specific case, how do I condense my numerator? How do I combine like terms? Well, I need what for fractions? I need common denominators. So I can multiply this one by x plus h over x plus h. I can multiply this one by x over x. I have to because it's not x times h, it's x plus h. So x plus h itself is one quantity. So I get 4x minus 4, I gotta distribute, so 4x plus 4h all over x squared plus xh. I just distributed it. Well, 4x minus 4x is going to be 0x. So all I'm left with is a negative 4h up top, negative 4h over x squared plus xh all over h. Okay. Well, again, it doesn't seem like I have anywhere to go. But now I just have two fractions, and we've divided fractions before. This is not just h, it's actually h over 1. And to divide fractions, keep change flip. So I get, let's see, I'm actually going over here. Negative 4h over x squared plus xh times 1 over h. Well, here's pretty nice because my h's would simplify out. So I get negative 4 over x plus h. I actually don't want to separate that. Now let's see, what can I do? Let me take a look at the book quick, I apologize. Yeah, not my original notes, I should have reviewed it a little bit harder. Oh, I do actually want to keep them together. x squared plus xh. And remember, this is the limit as h approaches 0. My original concern is I couldn't just plug it in because it's a denominator, but I can just plug it in because it's not the only thing in my denominator. Right now, it's only affecting this term. So I can just plug it in. So I get x squared plus x times 0. So my slope would actually be negative 4 over x squared. And that's a perfectly reasonable answer if we weren't given a very specific point. If I was, like, x equals 3, I could just plug it in, I would get negative 4 ninths or something. But because I wasn't given a coordinate, I can just do that. That will actually model the slopes at any given spot. And based on my x value, they would be different. So if I had 1, negative 4. If I had 2, it would be negative 1. The slope's constantly changing. That's all I got for you. All right. Thank you for listening. I hope you guys have a great day.